Good evening to one and all. Today in this live lecture we shall see or we shall prove the basic operational properties of Laplace transformation. In the last lecture we have seen in the basic operational Laplace transformation there are 6 different properties, 6 different theorems we have seen. Now we shall discuss the next Laplace basic operational properties. These are the some important special types of Laplace transformation of some functions. Now see here. Now we shall discuss some important definition regarding the Laplace transformation. See this definition number 1. Piecewise or sectionally continuous functions. Piecewise means in the part of, suppose a function is from, domain of the function is given from x is equals to 0 to infinity. In that domain there are some discontinuous point, and other than that discontinuous point we can take the function is continuous in the piecewise. So now we shall discuss the definition regarding the piecewise sectionally continuous function. 1 minute. A function f of t is said to be piecewise continuous on closed interval AB if it is defined on that interval and it is such that the interval can be subdivided into a finite number of intervals in which f of t is continuous, which has a finite right and left hand limits. See this. This is the definition of the sectionally continuous function. Means a function which is a continuous in piecewise. Suppose we have given the domain closed interval from A to B. Then overall in the domain there are some few points at which the function is discontinuous, but other than that discontinuous points we shall take the function as a continuous function. Okay, we shall suppose that we shall consider the function f of t is equals to, now see this, t square plus 2t plus 1. Check this one of the example. Divide by t minus 3, t minus 1, t minus 5. Student, now who can tell me this given function f of t is discontinuous at which points? Chalo, students, now you tell me this function is discontinuous at some points. Which are those? Chala re sanga. We have to find out the discontinuous points. आता हे आपल्याला discontinuous points कुठं कुठं आहेत हे चेक करायचे. तर कोण सांगेल? So this function is discontinuous at t is equals to, who can tell me? Very good. Keshav Ghadge, very nice. This function is discontinuous at t is equals to 3, t is equals to 1, t is equals to 5. Means at these values denominator goes to 0. And if denominator goes to 0, then the function is discontinuous. Now in this way, suppose whatever may be function, whatever may be, suppose this is a function f of t. Now this function is discontinuous at 1, then 3 and at 5. Here this function is discontinuous, means breaks at 5, breaks at 3, and this function breaks at 1. Means there is a gap. At x is equals to 1, at suppose this is a t, we consider this is a t, and this is f of t. Now this is a given a function f of t, graph of this function. This function is breaks at a point 1, 2, 3. But this function is continuous in the piece open interval 1, 3. This function is also continuous at a point 3, 5 and minus infinity to. So the function is piecewise continuous, minus infinity to 1, then 1 to 3, then 3 to 5. These are the subintervals at which the function is continuous, and 5 to infinity. See this, 5 to infinity. So these are the pieces of the domain at which the function is continuous. So such continuity is called as a sectionally continuous or the piecewise continuous. Okay, now we shall move towards the next. Function of exponential order. This is the second definition you must know. This is the particular function. A piecewise continuous function f is said to be exponential order C0 if there exists a real number C0 such that limit t tends to infinity mod of f of t into e raised to ct, which gives the value 0 if c is greater than C0, and which gives the value infinity, that means no limit, if c is less than C0. This is the this is the particular type of a definition you must know. This limit may or may not exist if c is equals to C0. If the function f of t is a function of exponential order C0, then we can write O of e raised to C0 into t. This is the exponential order function. You have to note that you have to discuss this definition, exponential order function. If that function satisfies the condition limit t tends to infinity mod of f of t into e raised to ct, which is equals to 0 if c is greater than C0, and it has no limit if c is less than C0, then the exponential order function, which is denoted by O of e raised to C0 into t. These are the few notes you must know. The function f of t is equals to e raised to a t is exponential order. C0 is equals to, here in this case C0 is equals to a, since limit t tends to 0, e raised to a t into e raised to minus ct is equals to 0 if c greater than 0. Second, you must know the function f of t is equals to e raised to t square is not exponential order if limit t tends to 0, e raised to t square into e raised to minus ct is equals to infinity. Then we can say this is the exponential, not exponential order for every real number c. Next, third, every bounded function t is exponential order C0 is equals to 0 since limit t tends to 0 mod of f of t into e raised to minus ct, which is equals to limit t tends to 0 m into e raised to minus ct. See this, m into e raised to minus ct, because this is a bounded function. If a function is bounded, then we know that according to the definition of a boundedness of the function, mod of f of t is less than m, for less than or equals to m, whatever may be, then it is called as a bounded function. So you can replace this as a m and e raised to ct, and which is equals to 0 if c is greater than 0. This is the condition. Okay, 1 minute. Next, 4 note, if a function f of t is order e raised to c naught t, exponential order function o of e raised to c naught t, then f of t is of order e raised to c1 of t for c1 is greater than c naught. Then some unbounded functions that increases like t raised to n greater than 0 are also exponential order. Next, there is another separate definition, that is a function of class A. A function which is a piecewise continuous on every finite interval t greater than 0 and is exponential order is known as, see this is the particular definition, function of a class capital A. A function which is a piecewise continuous on every finite interval when t greater than 0 and is exponential order, then it is known as function of class A. Next, we shall move towards one important theorem. Theorem number 5, that is a Laplace transformation of derivative. That means how to find out the Laplace transformation of a derivative of the function. See this. If the statement of the theorem is, if f dash f double dash dot f raised to n minus 1 means n minus 1th derivative are all continuous function, fn minus 1 are continuous function on t greater than 0, then fn is piecewise continuous on t greater than 0, and if all are exponential order e raised to c naught t, then for n is equals to 1, 2, 3 dot Laplace transformation of fn of t, we can write that as p raised to n capital F of p minus p raised to n minus 1 small f of 0 minus p raised to n minus 2 f dash of 0 dot minus dot minus fn minus 1 of 0. This is our proof, that is a derivative Laplace transformation of the derivative. See this is the definition, this is the statement of the theorem. Now we shall prove this theorem by step by step. But first of all, you must know which is the statement, what is the meaning of a statement for Laplace transformation of the derivative. Actually, this is a very simple theorem. One can understand this theorem, okay? But important condition is given, f dash f double dash dot fn minus 1 are continuous function on t greater than or equals to 0, comma fn is piecewise continuous on t greater than 0 if for all exponential order function e raised to c naught t. Okay, now we shall prove this theorem. Now we shall prove this theorem by the method of induction. Method of induction means what? First of all, we have to prove this result is true for n is equals to 1. This result is true for n is equals to 2. This result is true for n is equals to 3. In this way, we can show that this result is true for any value of n. Such method of proving the theorem is called as a induction method. You have to know this. Okay. Now we shall prove this theorem by the method of induction. Now we shall prove for n is equals to 1. If we put n is equals to 1 in the statement of the Laplace theorem, then we get n is equals to 1 means first order derivative. N is equals to 2 means second order derivative. This is not an index. You have to know. N is equals to 1, 2, 3 means this is the first order derivative, second order derivative, third order derivative. So now we shall consider for n is equals to 1. That means we have to prove for n is equals to 1. 1 means first order derivative. Laplace transformation of if we put n is equals to 1 here. Say this. N is equals to 1. Then what will happen? F dash of t, first order derivative. 1 means first order derivative. L of f dash of t is equals to, if we put n is equals to 1, then p raised to 1, capital F of p, then minus I as it is, p raised to, see this, 1 minus 1, 0. Student, you tell me what is the value of p raised to 0? So, p raised to 1 minus 1 means 0. That gives a value 1, f of 0. Then if we put n is equals to 1, then what will happen? Then, see this, p raised to minus 1. So, all our remaining terms are goes to 0. All remaining terms goes to 0. So, we can write this for n is equals to 1. We can write, see this, 1 minute. Okay, very good. Bhagyashree Panchal, yes. Pranavati Kadam, yes, okay. Now, so this can be written as p into capital F of p minus f of 0. And this is a true for n is equals to 1. By the definition of the Laplace transformation, how we can write this? According to the definition of Laplace transformation, capital F of p we can write in this way. L of f dash of t, which is equals to integral from 0 to infinity e raised to minus pt into f dash of t dt, according to the Laplace transformation. See this, we have replaced only in place of f of t, f dash of t in the Laplace transformation definition. Then what will happen? Now use product rule of the integration here. To find the solution of this, we have to use the product rule of integration. Integration of u into v dx. What is the formula for the integration of u into v dx? Anjali Kamble, Praneta Meshar. What is the formula? First is it is integration of second minus in integration derivative of first into integration of second. So we have to use this formula and we have to calculate the integration of this function. So first is it is integration of second. First is it is integration of second means f dash of x integration, because integration is antiderivative, so its derivative removes due to the integration e raised to minus pt into f of t dt over the integration from 0 to infinity minus again derivative of first means minus p into e raised to minus pt, and integration of second means integration of f dash of t is f of t. So according to the u into v formula, we get this. Now students, this is the lower limit is 0, upper limit is infinity. So if we put the upper limit infinity e raised to minus pt, we have solved this number of times, so its value goes to 0. And 0 into any term means 0. Minus if we put lower limit e raised to 0, काय तेरे e raised to 0 ची value. If we put e raised lower limit means e raised to minus pt. If we put lower limit means e raised to minus p into 0 means e raised to 0. that is equals to 1. Okay. So this value goes to 1. Again, if we put e raised to इथं dt नको आहे, हे wrong झालं पहा, dt नको आहे इथं. Don't write this dt here. 1 minute. So by mistake I have written this dt here. So keep this lower limit. So f of t is equals to 0 plus minus into minus plus, take out p out of integral from e raised to 0 to infinity e raised to minus pt into f of t dt. So calculate this value. So minus f of 0 plus pi is it is. Again, this is the formula for Laplace transformation. We can replace this as capital F of p. Hence, we get the result Laplace transformation of f dash of t. By using the definition of Laplace transformation, we get Laplace transformation of f dash of t is equals to p into f of p minus f of 0. And already we get this result p into capital F of p minus f of 0. This result is obtained by putting n is equals to 1 in the statement of the theorem, and this result equation 2, which is obtained by using the Laplace transformation, definition of the Laplace transformation for f dash of t. So both results are same. Hence we can say that the result is true or theorem is true for n is equals to 1. Result is true for n is equals to 1. Similarly, we can similarly as f and f dash are continuous, f double dash are piecewise continuous for t is greater than 0, and all are of exponential order O of e raised to c naught t. By applying the result 1 to the function for f double dash, see this result is for f dash of t. Now we have to apply this result, that result for n is equals to 2 or second order derivative f double dash of t. Then we get f double dash of t is equals to p into L of f dash of t minus f dash of 0. See this. From this equation, we have to calculate, see this. We have to calculate for n is equals to 2 means f double dash of t is equals to p into f dash of t. In this way, we get the result as for n f double dash, then we will get the result is p into L of f dash of t minus f dash of 0. But we know that here. But we know that 1 minute. Actually, this is याला कसं लक्षात येते का तुम्हाला हे L of f dash of t is equals to, according to this result we can write this capital F of p. Capital F of p means according to the Laplace transformation L of 1 minute we can write this here. आपको ये समझ में आना चाहिए. This can be written as capital F of p. Also we can write in the form of Laplace transformation of f of t according to the notation form f of t. So we can write this also L of f dash of t, which is equals to p into L of f of t minus f of 0. So similarly for L of f double dash of t, we get p into L of f dash of t minus f of 0. So this result f dash of 0. So we will get this result in this way. Now again put the value of f dash of L of f dash of t from equation 1. So this is a from equation 1. Then we will get, now multiply by this, p into p means p square, p into f of 0 and f dash of 0. So L of f double dash of t is equals to p square into capital F of p minus p into f of 0 minus f dash of 0. So this can be also written in the simplified form, L of f double dash of t, which is equals to p square into capital F of p minus f dash of 0 minus f of 0. So this is the result. This is the result we can obtain by putting n is equals to 2 in this equation. If we put n is equals to 2, then we will get the same result. See this. F double dash of t is equals to p square capital F of p minus p into f of 0 minus f dash of 0. If we put n is equals to 2, n is equals to 2, then what will happen? P square, only I shall write the right side, p square into capital F of p minus p into f of 0 minus f dash of 0. So this is a true for n is equals to 1. This is a true for n is equals to 1. Okay. So, okay, now, all right. See this, hence, thus, the theorem is true or result is true for n is equals to 2. Hence, by continuous this process, we can write for any value of n. So, L of fn of t, which is equals to p raised to n capital F of p minus p raised to n minus 1 f of 0 minus p raised to n minus 2, means f dash of 0 dot 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 in this way minus p n minus f n minus 1 of 0, and hence proved. In this way we shall prove the given theorem. Okay, 1 minute. Okay, so now we shall start this. Now 6. Now theorem number 6. What is the theorem number 6? The existence of Laplace transformation. This is the theorem number 6. Now here we have to discuss theorem number 6. What is the statement of the theorem? If, 1 minute, if आवाज येतो का रे स्टुडंट्स? काय प्रॉब्लेम आहे का? आवाज येतो का रे? हाँ, ठीक है. If f is piecewise continuous on t greater than or equals to 0 and t is exponential order O of e raised to c naught t, the function f of t has a Laplace transformation capital F of p in the half plane real part of p which is greater than c naught. Moreover, the Laplace transformation integral converges both absolutely and uniformly for real part of p is greater than c2 is greater than c naught. See this is actually, you have to know the statement of the theorem particularly. तुम्हाला या theorem ची statement particularly समजली पाहिजे. थोडी लेंदी theorem आहे, लेंदी statement आहे. कंडिशन समजायला थोडी अवघड आहे. So see this again. If f is a piecewise continuous on t greater than or equals to 0 and t is of order e raised to c naught t, the function f of t has a Laplace transformation capital F of p in the half plane. Real part of p is greater than c naught. Moreover, the Laplace transformation integral converges both absolutely and uniformly for real part of p is greater than c naught is greater than, sorry, c2 is greater than c naught, c1. Okay, see this. Now, to prove the Laplace transformation of the function f of t exists, we have to prove that the Laplace transformation or integral capital F of p is from integral 0 to infinity e raised to minus pt into f of t dt converges. Actually, to prove the Laplace transformation of the function f of t exists, first of all we have to prove that Laplace transformation of the function f of t exists. To prove this, what we have to show? That we have to show that this integral exists, means we can find the value of this integral. Okay, 1 minute. Now we have capital mod of capital F of p. According to the definition of the Laplace transformation, we have taken the modulus value on both sides. So mod of capital F of p is equals to mod of integral from 0 to infinity e raised to minus pt into f of t dt. You know that mod of integration, which is always less than, there is one theorem which is always less than integration of mod of function. So according to that theorem, we can write which is less than or equals to integral from 0 to infinity mod of e raised to minus pt into f of t dt. Actually, this is the theorem by theorem. Which theorem? You must know, that is mod of integral from a to b f of x dx, which is always less than or equals to integral from a to b mod of f of x dx. This theorem we have studied in the UG second year. In the B.Sc class, we have proved this theorem. So we can write this, which is equivalent to e raised 0 to infinity e raised to minus ct, because here we have considered the real part of p is equals to c. The real part of this p is equals to c, so replace this real part as a c into t dt. In this way, f mod of f of t dt. Okay? Since f of t is exponential order, that is O of e raised to c naught t, and piecewise continuous on t greater than or equals to 0, then for given c greater than 0, we find a number c1 with c naught is less than c1 is less than c, and some to function to such that mod of f of t into e raised to minus c1t is less than epsilon. See this. This is the order where exponential function such that c naught is less than c is less than, sorry, c1 is less than c. So this is a less than epsilon. We consider this function as less than epsilon when t is greater than t naught. Hence, from equation 1, we have mod of f of p is less than or equals to integral from 0 to infinity e raised to ct into mod of f of t dt. Now we have to divide this into the two part, because t is greater than t naught. Then there exists a point c1, sorry. Then there exists a point c1. So we have to divide this integral from 0 to t naught and t naught to infinity. So we have divided this integral into two parts, 0 to t1, t naught, integral from e raised to ct mod of f of t dt plus integral from t naught to infinity e raised to minus ct mod of f of t dt. Okay, where the first integral with a finite limit exists, since the function f is piecewise continuous. F is piecewise continuous. Also, the second integral satisfies. Now, we know that for this is a continuous and limit is exist. First part, this limit exists. Now our aim is to solve the second integral. We have to discuss the second integral. So the value of second integral is from t naught to infinity, because first integral is convergent. We can find the value of first integral which is a continuous and convergent. So now our aim is to show the discuss about the second integral from t naught to infinity e raised to ct mod of f of t dt. We can write this. Here we have multiplied by e raised to, see this, e raised to plus c1t into e raised to minus c1t. That means we have multiplied e raised to c1t into e raised to minus c1t. That means which is equals to 1. So equivalent value we have multiplied e raised to plus c1t into e raised to minus c1t. Out of that we can take the common e raised to c1t and e raised to ct. We can take the common minus. So c minus c1 into t mod of f of t again as it is, and e raised to minus c1t as it is. Now this is the convergent, and we know that we have given the value, 1 minute. We have considered the value of this function is less than epsilon. Less than epsilon. So this term is a less than epsilon. So we can write in place of this epsilon. Epsilon is the constant term which is nearer about 0. So we can take epsilon outside of this integral. So epsilon, this value left side is less than epsilon into integral from t0 to infinity e raised to minus inner bracket c minus c1 into t dt. Now we can find the integration of this function also. We can find easily integration of this function. Who can tell me what is the integration of e raised to minus e raised to minus inner bracket c minus c1 into t? Who can tell me what is the integration of this function? Because in this case we can find the integration of this function directly. So this shows that we can find the integration of this function, means that converges. This, so here in this case first integration we can find the integration of first part. Similarly we have proved we can find the integration of second part. That means we can find the value of integration of this function mod of capital F of p, and this shows that we can find the value, or we can show the integration of this value converges, because first integration converges, second integration converges, therefore mod of F of p also converges, and this is the required proof. This integral exists if c greater than c1 from 2 and 3, and this shows that mod of capital F of p, which is equals to mod of integral from 0 to infinity minus pt into mod f of t dt exists or converges. We can find the integration, and this proves that the Laplace transformation integral converges absolutely. Similarly, it can be shown that the integral converges uniformly for a real part of c1. Here we have to write c1, real part of P is greater than or equals to C1 is greater than C naught. So you can write here in the last, real part of P which is greater than or equals to C1 which is greater than C, and hence proved. हा थोड़ा टिपिकल थेरम आहे, हा थेरम व्यवस्थित करा. व्हेरी गुड. शिल्पा पांचाळ करेक्ट आहे. प्रदीप जनमाले व्हेरी गुड. Thus we have proved the second theorem. Now note that here, this is a very important note you must understand. This is only a sufficient condition for existence of Laplace transformation, but converse is not true, or it is not necessary. It is not necessary. This is the sufficient condition, but necessary condition may or may not be true. Converse of this theorem may or may not be true. Note that. This is the theorem. Statement of this theorem is true only sufficiently. Necessarily, that means converse may or may not be true. He note लक्षात ठेवा. Now, to prove this note, for verification of the note, we have considered one example. See this. The functions t raised to -1 into t raised to -1 by 2 are not piecewise continuous on t greater than 0, but their Laplace transformation exists. See this. You know that according to the definition of the Laplace transformation, student, L of t raised to -1 by 2. You know that according to the definition, integral from 0 to infinity e raised to minus pt into f of t dt. F of t is here t raised to -1 by 2. So replace this value t raised to -1 by 2. Now we can extend this in this way, integral from 0 to infinity e raised to minus pt into t raised to -1 by 2. We can write 1 by 2 minus 1 dt. We have changed this value, -1 by 2. We can write in this way 1 by 2 minus 1. Student, you tell me what is the value of 1 by 2 minus 1? हा फास्ट सांगायचं, मला चेक करायचं असतं कोण कोण ऑनलाईन आहे ते. मी छोटे छोटेच क्वेश्चन विचारतो, पण मला हे पाहायचं असतं की कोण कोण ऑनलाईन आहे. सो -1 by 2 minus 1 means again -1 by 2. So we have shifted this value t raised to -1 by 2 in t raised to -1 by 2 minus 1. So we will get the result. How we will get this result? According to the Laplace transform, according to the gamma function, we can write t raised to n minus 1. According to the gamma function, we can write here t is also -1 by 2. Here t is also -1 by 2. Okay, ठीक है. F of t. Okay. Thus we get the gamma of 1 by 2 upon p raised to 1 by 2, and this result goes to root of pi by p. Means we can find the Laplace transformation of t raised to -1 by 2. We can find the Laplace transformation of t raised to -1 by 2. That is a convergent. We have this result show that Laplace transformation of t raised to -1 by 2 is convergent, but we know that t raised to -1 by 2 is not a piecewise continuous on t greater than 0. So this example tells us that this theorem is satisfies only for the sufficient condition, we can't say about a necessary condition. It may be true or may not be true. Now next we shall see the next theorem, theorem number 7. Okay, theorem number 7, Laplace transformation of the integration. Already we have seen in the theorem number 5 what is about the Laplace transformation of the derivative. Now we shall see what is about the Laplace transformation of integration. Again, we shall move towards, if f is a piecewise continuous on t greater than or equals to 0 and of order e raised to c naught t, then we have to prove that, or then prove that Laplace transformation of integral from 0 to t small f of u du, which is equals to capital F of p divided by p, where capital F of p is Laplace transformation of small f of t. This is also a simple theorem. Now we define a function. First of all, we have to define a function. Small g of t is equals to integral from 0 to t capital F of u du. Here f is piecewise continuous on t greater than 0. It follows that g is a continuous. Now see this 1 minute. Okay. Now also f of g is equals to 0. G dash of t is equals to capital F of t. Hence, by the theorem, L of f of t is equals to Laplace transformation of g dash of t. See this capital f of t. G dash of t is equals to f of t. See this according to the definition. See here, whatever may be. Suppose g of t is equals to integral from 0 to t f of u du. If we differentiate this, then g dash of t is equals to f of u, but limits are from 0 to t, so we can write f of t. Thus we can write g dash of t is equals to f of t when g of 0 is equals to 0 according to the initial condition. Hence, by the theorem, now this we can apply the Laplace transformation of this function. So L of f of t is equals to L of g dash of t. So L of f of t means we can write capital F of p, which is equals to L of g dash of t. Already we have seen in the theorem Laplace transformation of derivative of a function. See this in this function. Already we have seen here in this equation 1. See this. L of f dash of t is equals to capital P into capital F of p minus small f of 0. By using this statement, for n is equals to 1, in the derivative of Laplace transformation, we can write here in this case L of g dash of t means capital P into L of g of t minus g of 0. So, but we have given g of 0 means, which is initial condition, 0, that is 0. So what is the remaining term? L of capital F of p is equals to p into L of g of t. So transfer this p on left side. Then remaining term is L of g of t is equals to capital F of p upon p. That means L of g of t, which is equals to, according to the definition, we can write L of g of t, we can write this function g of t. So this can be written as 1 minute. G of t means we can write this. G of t means this. So we will get the result as, keep this L as it is. L of g of t means integral from 0 to t f of u du, and right side is as it is. And this is our required proof. This is our required proof, means This is actually L of, and hence proved. Hence proved. हे theorem परत एकदा पहा, खूप simple theorem आहे. Actually this is a very simple theorem. We have to prove that L of integral from 0 to t f of u du. So this function first of all consider by small g of t. That means we have to replace this as small g of t. Then we have to prove L of small g of t is equals to capital F of p divided by p. This is our main proof, and we can prove this by the theorem series. Now, okay, this is a L of integral from 0 to t f of u du. Okay, if you have any doubt, then you can ask me. Now we shall prove this note. Note, this is a second important note you must know. From the above theorem, we observe that the operation of differentiation and integration in the p domain corresponding to the algebraic operation of multiplication and division in the p domain. Multiplication operator, and see this again. Note, see this important. From the above theorems means which theorems? Theorem on Laplace transformation of derivative, theorem on Laplace transformation of integration. By using these two theorems, we can say that in the p domain corresponding to the algebraic operation of multiplication and division in the p domain. That means here in this case, p is in division and in this case in the derivative. In the derivative condition, p is in multiplication. See this, p is in multiplication. Here p is in multiplication. So this note tells us that, समजतंय का पाय हे का मल्टिप्लिकेशन आणि डिव्हिजन मध्ये लॅपलास ट्रान्सफॉर्मेशन च्या थेरम मध्ये लॅपलास ट्रान्सफॉर्मेशन ऑफ डेरिव्हेटिव्ह आणि लॅपलास ट्रान्सफॉर्मेशन ऑफ इंटिग्रेशन, the role of p in the domain p domain, we get multiplication and division. Okay, हे थेरम एक दोन वेळा पहा, रिवाइज करा. काही अडचण आली तर विचारा, कॉलेजमध्ये येऊन विचारा. एखादी स्टेटमेंट या थेरम मधली जर नाही समजली तर कॉलेजमध्ये डिपार्टमेंटला येऊन विचारू शकता. व्यवस्थित नोट वगैरे काढून हे पहा रे, सर्व विद्यार्थ्यांच्या नोट्स जेव्हा तुम्ही असाइनमेंट्स पाठवतात ग्रुपवर तेव्हा असाइनमेंट्स व्यवस्थित मिळत नाहीत. यू हॅव टू राईट असाइनमेंट्स प्रॉपरली अँड देन सेंड इन द व्हॉट्सअप ग्रुप. ओके, unless I don't consider your assignment, your note. Okay, समजतंय का रे? लक्षात आलं का? काय अडचण आहे का सांगा. ठीक आहे. Now we shall stop here. We shall see the next problems. Actually these are the theorems which is here. I shall write this theorem number first here. Theorem number, what is that theorem? Theorem number 6. Theorem number 7. See this. This is a theorem number 7. This theorem number 7 is based on Laplace transformation of integration, and this theorem number, I think 5. Theorem number 5 is based on Laplace transformation of derivative. See this, Laplace transformation of derivative. Okay, काय विचारायचे का रे कुणाला? If you have any question, then you can ask me. ठीक आहे. तर असो, we shall stop here. प्रदीप जमाले, कांबळे, गौरव इंगळे, प्रणवती कदम, ओके, तर इथं आपण थांबू. नाउ वी शॅल सी द नेक्स्ट पार्ट based on the problems. Okay, and the problems are depending on the basic properties and these theorems. Now we shall see later on. Okay, good night.